So I'm continuing from um, the previous video that I did on evaporation. This one is on infiltration. So it's just a brief, and I'll just explain the concept, what infiltration is about, and just a few basics. More details can be found on the texts I have provided for you. So, what is infiltration? Infiltration is just water entering the soil at the ground surface. Okay, water entering through the soil at the ground surface after it has satisfied evaporation and all the other components of hydrologic cycle. Now, I will throw this up to show you what we see, what we mean by the concept. So, we have rainfall coming in. There is interception of some of the water by leaves of trees, by roofs, and then there's some evaporation going on. Then, after evaporation and all these interceptions, the rest of the water that hits the ground is what we call effective rainfall. Now, when the effective rainfall hits the ground, it must fill what we call depressions first, and then once it fills the depressions, uh, there will be some components that will also be infiltrating. So this depression storage, first of all, must be satisfied on surfaces that have depression. Then after they are satisfied, then some water will start infiltrating to the ground, and some can percolate into groundwater. Some will move through shallow areas of the ground to what we call interflow. And then once the rainfall amount is able to overcome depression storage and infiltration, then the rest will start running off. So runoff will only happen after infiltration has been satisfied, or let's say the ground's test has been satisfied, then the rest can start running off. So this is a conceptualization of the role of infiltration in runoff generation, and the importance of infiltration in the entire um, water cycle or in hydrologic studies. So when uh, infiltrations occurs, this goes to satisfy soil moisture lost for plant usage, or it further goes down to satisfy groundwater recharge, okay, so that groundwater tables can rise. Now, the diagram you see here is a theoretical diagram of infiltration. This is based on what we call Horton's model. So what you have here is a curve, an infiltration equation curve that is falling with time. Now, let me use this to explain it further. So normally when rainfall starts, the initial infiltration rate is often very high. As time increases, the infiltration rate will start reducing because the moisture conditions are being satisfied, and the more the ground is able to drink more water, the less the infiltration rate, until it gets to a point where the infiltration rate approaches what we call constant infiltration rate. So this line you see here is it's a natural logarithm line that drops with time, and then as time goes on, it virtually becomes constant. And at that time where it becomes constant, that that this infiltration rate or final constant rate can be equated to the um, hydraulic conductivity or the permeability of the ground, especially at times when the ground is saturated, because we all know permeability in soil mechanics or hydraulic conductivity is determined at times when soil becomes saturated, and that is what happens around this area. So that is what we call the Horton's model, and that is what happens. So um, that is now the maximum rate at which a soil is able to absorb water is what we call its infiltration capacity. In fact, it should be the maximum rate, yes, at which the soil is able to absorb water is the infiltration capacity. Okay, so and this, as I've just shown you, varies with time. Okay, so what factors does infiltration depend? Infiltration is affected by several factors. The first factor that affects infiltration is soil texture, which is a fact which is based on the porosity and the permeability of the soil. So the porosity is how much water the ground can store. So if you have a soil like clay and a soil like sand, because sand is less porous than clay but highly permeable, that comes to play and the ground will start, let's say, drinking water or infiltrating a lot of water uh, as compared to clay. Uh, so, for instance, if you compare, you take clay for instance, because the porosity is very high, it will store, it doesn't release water quickly because its permeability is low. The infiltration for, say, clay compared to soil under the same conditions will be very low because clay does not allow water to permeate, but it rather it stores. So if water, previous water sitting there, sitting moisture is already stored, then you should see you are going to observe an infiltration situation which is very slow compared to, say, sand, because the water is not moving away. The next point is antecedent soil moisture content. So the previous moisture content. If the ground is already saturated with some water, then the filtration rate is very low. But if the ground is dry, I'm assuming the last rain was 6 months ago, the initial infiltration rate will be very high until saturation conditions are reached. But if the ground was already wetted about a few days ago through rainfall, then you're going to have a slow rate of infiltration. It also depends on rainfall intensity. The faster the rainfall intensity, the higher the rainfall intensity, the the higher the infiltration capacity or the infiltration rate. And then the vegetal cover is also a factor of the cover crop or the covering on the soil. So if the soil is covered by, say, cover crops like legumes, cocoyam, cover crops, then you're going to have low infiltration rate. If the ground is bare, then there's going to be very fast infiltration rate because the ground is going to be heated directly by the soil, by water. But normally, sometimes this bare ground can also be a negative feedback effect because sometimes when initial rains come, because the ground gets moisturized, it gets to a point where we have something like a protective layer of uh, a wet layer trying to protect uh, the the dry layer, and there is this feedback process. But by and large, this is also a fact. Vegetal cover or how much vegetation covers the ground plays a role, and then the degree of compaction is related to how much the ground is compacted. So as I was trying to point out, the even in some bare ground, sometimes when the rain comes, after a while the rain beats the ground in such a way that the ground becomes compacted and then it starts negative feeding back, and then infiltration rate starts reducing. So degree of compaction is how much the ground void spaces are covered or they are closed up. If you have highly compacted soil, infiltration rates are low compared to loose soils. Okay. So these are the factors on which infiltration rate depends. Now, in in analyzing in analyzing uh, infiltration rate, we have what we call infiltration indices. This is well highlighted in the hydrology text I've given to you. So um, there are some concepts we use to determine infiltration capacity And once we determine infiltration capacity, we have a technique to determine how much runoff is occurring. And you can even use this to determine what we call the runoff coefficient. So when it starts raining, I know you already know what this is. This is a yetograph of rainfall. Okay, so if you have rainfall occurring and infiltration rate is known, then if you draw the infiltration line, the infiltration rate is just like the intensity, rainfall intensity. Okay, so if you have the infiltration rate intensity, it's also calculated in centimeters per hour or centimeters per second or whatever. So if you're able to put on the infiltration rate for um, a rainfall pattern, any line, any part of the rainfall or any part of the rainfall intensity above the infiltration line is the runoff. So here, what you see is these lines you have here, which is the phi line and the W line, are infiltration capacities. And normally we assume that they are constant. But as you can see from the Hortonian model, infiltration rates are sometimes not constant. So this is one of the indices we use. But the thing is, if you're able to determine the Hortonian profile, you can put the profile on and still find out the runoff amount, any line above the infiltrate. So um, let me set, imagine I put a line here like this, right? Anything above this line here, anything above this line, let me make this a little bit. Anything above this blue line here, okay, this blue line here is your infiltration. But um, we can either use the Hortonian model to put in our infiltration curve, or we can use what we call the phi index, which is what I've put here, which is the phi index is defined as that constant rate of infiltration that will yield an excess rainfall whose total depth of rainfall is equal to the total runoff. So if you put on uh, the phi index, this line here, this line here, this one, which is the phi index, then you can, any line above it is your filtration rate. And that is the first indices we use to determine infiltration capacity. Once we know that, which is a constant rate, we can use that to determine the runoff. Alternatively, we can also use the Hortonian model, which is a curve and varies through time to determine the runoff. And there are parameters that we can be given to enable us determine this. If you look through the text on page 35 and so on, in the handout that I've given, which is the lecture note, and in the hydrology note, you can get more information about that here. But by and large, the phi index is defined as basin recharge over duration of rainfall. And the basin recharge, okay, is the basin recharge. Okay, so the phi index in itself, okay, can be analyzed as uh, infiltration. Infiltration minus the phi index gives you the P net. The P net is the uh, precipitation net, okay, which is this area under the curve, this area. What do you have here? So after the ground has drank all the water, precipitation minus the storm loss, precipitation minus the storm loss is what gives us our P net, okay, which is the storm loss is the infiltration. So precipitation minus the storm loss gives us what we call the P net, which forms what we call the runoff in the catchment. So you can either use the phi index concept, which has been demonstrated here. Okay, so once you're able to determine the infiltration rate on our curve, then we are able to uh, um, determine how much runoff. But you see what happens in reality or in real practices. Runoff is easy to determine. Okay, runoff is sometimes easier to determine because we can have gauges at different areas of the catchment, and from this gauging we can determine precipitation amounts, and we can determine runoff amount. Once we know runoff amount and we know the total yetograph, we can now insert the runoff positions to determine our. Once we are able to balance the runoff of the total yetograph, what is left gives us our find, which tells us our infiltration rate, and we can actually use it directly to relate to how much water is recharging groundwater for groundwater tables to rise. Okay, so once we know this, we can. But the thing is, in this our syllabus, we are not really determining fine indices. You're supposed to just have an introduction of it, which eventually will be built up when you get to the degree level or when you want to top up. The other model is what we call the Hortonian model, which is a model that describes infiltration rate changing with time. And this is really what happens in reality, not what we have as the constant phi index that I've already seen. But this serves when you have very simplified catchment analysis. This can also still give you very good estimates, especially if the rainfall rates don't change, or if the especially if the infiltration rate does not change so much from the initial conditions. But the point is, in reality, this is what happens, which is the Hortonian model. Uh, I would advise that you look at the rest of the lecture slides I've been put there. I've put on the portal to analyze the advantages and then the disadvantages of each of the models. I think these are examinable, but using the models or the indices to determine direct amount of infiltration is not examinable. What you're supposed to know per our syllabus is for you to know about the indices and the concepts and how they come up in our derivations. Um, I think this should be our final note. So I will be glad, I'll be happy if you can go through these slides quickly and this video quickly and give me feedback so that I can find a way of improving on these videos. In fact, it's difficult to just speak to yourself when you have those students sitting before you. So please provide feedback so that I can find ways of improving the presentation. Thank you very much.